Hello everyone, welcome to Lab 9, in which we will discuss two other methods for integration. In today's lab, we will review Romberg's method for integration and Gauss quadrature, and also I'll be giving out some assignment tips on how you can perform analytical integration using integration by parts and change of variables which you need for Gauss quadrature in some cases. So you were introduced previously to Romberg's method in the lectures, and it involves using two less accurate trapezoidal approximations to obtain a more accurate approximation of the integral. So this is the mathematical form of Romberg's method, and its full derivation is already in E-class in the lecture notes. And as you can see here, the table shows you how to implement the method. So the first column of the table simply involves evaluating the integral using the trapezoidal rule. So up to this point, up to this column, nothing new is here. So you're simply calculating the integral using the trapezoidal rule with a step size of h1. Here you're calculating it using step size of h1 over 2, h1 over 4, h1 over 8, and so on. And by using the two approximations, we're able to increase the accuracy level of our estimate from OH squared to OH to the power 4. So we're simply using the two approximations to end up with a better approximation, and so on. We're using the two approximations to move on to a higher approximation, highly accurate approximation. And this is how we apply the Romberg's method. You already have this code on E-class, and this is from example 11.6, and I decided to walk you through it since you're required to come up with something similar in the assignment. So starting from line 25, we start to implement the table, which I've previously discussed. So the while loop starts with defining the stopping criteria, which is based on the error threshold and the maximum number of iterations. And then this loop calculates the first column of the table here. And as you can see, it's nothing but calling the trapezoidal function, which you already have in E-class, and using it for different steps. So we're basically calculating the integral using h1, which is equal to h, and h2, which is equal to h over 2, h3, which is equal to h over 4, and so on. So we're basically calculating different integrals using the trapezoidal rule with different step sizes. Starting from this point, we use two nested loops in order to move from one level using Romberg's method. So this loop calculates Romberg's method for a column, and then we reiterate over it using the other loop in order to move from one column to another. And then we keep repeating this process until we reach the desired level of accuracy based on the error threshold. As it was mentioned in the lecture, Gauss method is a very powerful technique that can be used to approximate a definite integral I of a function f from the limits of -1 to 1, and this is done by replacing the integral with a discrete summation of the product of a certain weight, w of I, and the function evaluated at a certain integration point x of I, and this can be mathematically written in the following form. This table was introduced in the lecture, so this is the number of integration points that you're going to use, and it also determines the polynomial degree that you're using for Gauss method. So if you're using one point or one integration point, your integration point will be at xi equal to 0, and the weight of it will be equal to 2. So you simply you evaluate the function at 0, and you replace the weight with 2. If you decide to use higher number of points or higher degree polynomial, the integration points would be of the following form, and the weight will they will have the following weights. Notice that if the function you're trying to estimate is already a polynomial, and if you use an appropriate number of integration points, then the result will give you the exact solution like the analytical solution. So for example, if you're estimating the integration of a second degree polynomial and you use 2 integration points, the result would be an exact result. So I wanted to demonstrate how you can simply perform Gauss method in MATLAB. You already have a code on eClass that employs tables and so on, and I recommend you that you see it and compare to this method. But this is another method, and you can definitely have more than one way of writing this code or the code in eClass. So you start off by defining your inputs, which is in this case the order of the number of integration points. Here I'm using an order of 2. And you need to define your function, and I defined it as an anonymous function. In this example, I'm using x to the power of 2, which is x squared. And you should note that the exact solution for this integral would be equal to 2 over 3. So I'm simply performing the integration from -1 to 1 of x to the power of 2. And then I'm using the switch function in MATLAB. So it's a feature of the MATLAB language. So basically I'm telling MATLAB to evaluate the case, whether it's n equal to 1 or n equal to 2. And then if n is equal to 1, then my integration point will be equal to x equal to 0, and it will have a weight equal to 2. If x is equal to, if n is equal to 2, then x will be equal to 1 over square root of 3, and -1 over square root of 3, and it will have a weight of 1 and 1, and in this case they are defined as a vector. And then to simply evaluate the integral, all you have to do is to take the summation of the element by element multiplication between the w, which is the weight, and the function evaluated at the integration point. And that's the MATLAB's format in which you can write this simple code. And just for some displaying purposes, I wrote the exact value. And if we run the code here, as you can see that the exact value is 2 over 3, and I'm using an order of integration equal to 2, and the Gauss integration as expected gave us exactly the same results as the exact solution because I'm using an appropriate number of integration points. I wanted to conclude this lab by giving out some assignment tips. The first one is about integration by parts. So in some cases you can evaluate integrals analytically using this method, and it's quite analogous to the product rule of differentiation. So when your integral is composed of the product of two functions, you can use integration by parts. And this is the mathematical form. As you can see, the integral is composed of the product of u and v prime, where u and v are both functions of x. And if this is the case, you can express the integral as the product of u and v minus the integration of u prime multiplied by v dx. In this case, it's particularly useful to choose u to be a function that is simplified by differentiation. So let's demonstrate this by an example. As you can see here, the integration is composed of x and multiplied with cosine of x. If I choose u equal to x and v prime is equal to cosine x, you'll notice that u becomes 1, which means that it's becoming a simpler function by differentiation. That's why I chose u to be x and not cosine x. So we express the integral using the integration by parts rule into these two steps, and then you can find the final results as the following. Finally, I wanted to remind you that the Gauss method that we discussed earlier assumes that the limit of integration is from -1 to 1. So if you have a more general case where the limits are from a to b and you want to integrate the function, all you have to do is to do a simple change of variables, and this was introduced in the lecture. This is the form, or this is how you do the change of variables using the limits. And this is one example that shows how you can do that. So the limits of integration are from 0 to 3, and by using this change of variables, we're able to express the function in the following form and do the integration from -1 to 1. So this is the function that you insert into MATLAB. Okay, thank you for watching the video and hope it helps you.